For weeks, astronomers have been stunned as objects nearly 100 times bigger than expected keep multiplying in the sky. Now, as the interstellar traveler 3I/ATLAS makes its approach toward Mars, the mystery has only deepened. Are we witnessing a cosmic coincidence, or is something far stranger unfolding beyond our planet? Stay tuned, because what scientists are seeing might change how we understand the dangers above us. When the sky broke its pattern. For decades, astronomers have trained their eyes on the night sky, counting objects that skim past Earth. Usually, the pace is predictable. A handful of small near-Earth objects glide by each month, their passages quiet and often unnoticed outside specialized circles. But between September 12th and 18th, that pattern collapsed. Telescopes across the globe registered a sudden and unprecedented surge. 28 sublunar objects, each traveling inside the orbit of the Moon, were catalogued in just 7 days. In statistical terms, this was not simply unusual. It was a spike that bent the curve of what science thought it understood about asteroid traffic. Survey teams were the first to feel the weight of the anomaly. The Rubin Observatory, still fine-tuning its all-sky monitoring, streamed data into shared pipelines. Atlas, Pan-STARRS, and Catalina joined in, their automated software blinking with new detections faster than scientists could verify. Normally, each discovery is logged, cross-checked, and slowly digested. But in this week, the pace became dizzying. What usually unfolded over months was compressed into hours, leaving scientists with the sensation of chasing a sky that no longer obeyed its own rhythm. This flood of detections triggered not only excitement, but a sharpened sense of vulnerability. A sublunar passage means an object slides between Earth and the Moon, sometimes much closer. Even a rock just a few dozen meters across can carry the explosive potential of hundreds of thousands of tons of TNT. The September surge forced experts to ask if they were witnessing a statistical fluke or if deeper gravitational forces were herding small bodies into Earth's path. Some speculated about clustering effects in near-Earth space, temporary resonances that corral loose debris into streams that brush against our world. The numbers told their own story. In earlier years, weeks like this were virtually unknown. Data records reveal occasional bursts, but nothing approaching the density of this one. It was not just the count, but the size range that caught attention. A few of the bodies were large enough to penetrate the atmosphere and explode with dangerous force if they had crossed Earth's trajectory just a little differently. For survey teams used to the quiet routine of discovery, the week felt like a drill run by the cosmos itself, reminding them of the fragility of prediction. Yet the week's drama was not confined to scientific databases. Once public feeds began sharing detection lists, the phenomenon spilled onto social media. Charts spread rapidly, with enthusiasts overlaying orbital tracks across Earth-Moon diagrams. For the first time, a wider audience began to grasp what astronomers had quietly managed for decades. Near misses are far more common than the public assumes. That realization stirred both fascination and unease. If so many small objects could skim by in silence, what about the ones still unseen? The pressure on observational networks became a race against time. Teams worked through nights, shifting telescope priorities and recalibrating software filters to separate genuine near-Earth objects from the noise of false detections. Each confirmed pass was like another bead strung on a necklace, a growing chain of evidence that the week of September 12th was no ordinary episode. What unsettled many scientists was not the presence of one large object, but the sheer accumulation of smaller ones. Each alone posed limited threat. Together, they formed a pattern that hinted at processes not yet fully understood: gravitational nudges from larger planets, fragmenting parent bodies, or still undiscovered resonances within the solar system. These possibilities meant that the September surge could be the first visible signal of a broader celestial dynamic unfolding in real time. If a week can produce this many near misses, what would one close call actually look and feel like? Stay with us to uncover the details. If FA22 hadn't missed. Imagine waking up to a blinding flash in the sky, brighter than the sun, followed by a shock wave that shatters glass for hundreds of kilometers. For millions of people, it would feel like the end of the world. Yet this nightmare scenario is not fiction. It is the direct consequence of an object like FA22 striking our planet. FA22 and its companion RJ2 were not anonymous specks on astronomers' lists. They were giants compared to the background swarm of small near-Earth objects. FA22 stretched the size of a city block, large enough to release an energy burst that would dwarf any nuclear weapon ever built. Scientists quickly ran simulations. If its trajectory had intersected Earth's atmosphere, the event would have been catastrophic. Unlike the harmless streaks of smaller meteors, FA22 carried the weight to level a city or ignite regional chaos in seconds. To understand the danger, one must look at how impacts unfold. A stony asteroid of FA22's size would not glide gently into the atmosphere. At speeds exceeding 20 kilometers per second, the air becomes a wall of fire. Friction transforms kinetic energy into heat, building unbearable pressure inside the object. The result is an explosion in midair, often at heights between 15 and 30 kilometers. This is called an airburst, and its destructive power spreads outward in shockwaves. The comparison to Chelyabinsk is chilling. In 2013, a smaller body, only about 20 meters across, detonated above Russia. Its shockwave injured over 1,000 people and shattered windows across 6 cities. FA22 was estimated to be more than 10 times larger. Instead of broken glass, entire neighborhoods could have collapsed. A detonation at that scale could flatten forests, rupture gas lines, and spark fires that spread for miles. And what if FA22 were not made of stone, but iron? Iron bodies behave differently. Instead of breaking apart high in the atmosphere, they often plummet intact to the ground. The result is not an airburst, but a crater, an excavation of Earth with the force of thousands of megatons of TNT. Scientists noted that an impact in ocean waters could generate tsunamis large enough to devastate coastal cities across multiple continents. The type of composition becomes the difference between a shockwave in the sky and destruction that ripples across oceans. Historical scars show us what is possible. The Tunguska event of 1908 flattened 80 million trees across Siberia. The culprit was a rock smaller than FA22. For weeks afterward, the skies of Europe glowed at night from dust ejected high into the atmosphere. That was an uninhabited region. Imagine the same event above New York, Tokyo, or Mumbai. The devastation would not remain a local disaster. It would shake the global economy, trigger humanitarian crises, and rewrite geopolitics overnight. What makes these threats even more unnerving is the speed at which they approach. Objects like FA22 are often discovered only days before their closest pass. The September surge highlighted how even advanced surveys can be caught off guard. While FA22 did not strike, the margin of safety was far narrower than most people realize. For astronomers, each close pass is a reminder that detection is not enough. Without preparation, discovery buys little time. The story of FA22 and RJ2 is not just about what might have been. It is also about the thin line between vigilance and vulnerability. Emergency planners quietly discuss impact scenarios, drawing up models of evacuation routes and resource needs, but few governments have tested these plans in reality. For the public, the conversation remains distant, hidden behind jargon and orbital diagrams. But for scientists, the week of FA22's approach became a stark rehearsal of what the future might deliver without warning. We can model catastrophe, but can we detect every kind of threat early enough to act? Come with us to find out more. The UV alarm SWAN sang before the tail appeared. The alert did not come from a telescope scanning invisible light. It arrived from space through a silent ultraviolet whisper. The solar wind anisotropes, SWAN instrument aboard the SOHO spacecraft, detected something odd. A sudden, concentrated surge of hydrogen atoms glowing in Lyman alpha light. Before any comet was visible to the naked eye, the cosmos had already begun singing its signal in ultraviolet. Astronomers have long depended on visible light surveys to track comets and asteroids, but SWAN's detection revealed a critical truth. Not every visitor announces itself with the shimmer of reflected sunlight. Many carry volatile gases that interact with solar radiation, releasing ultraviolet signatures far earlier than tails or comae appear. This particular detection forced scientists to rethink how alerts should be handled. If ultraviolet instruments can see a threat before the optical surveys do, then the window of warning could widen in ways that save lives. The object under scrutiny began releasing enormous amounts of hydrogen, suggesting violent activity within its core. This was no quiet traveler. It carried volatile-rich ices that sublimated explosively when exposed to sunlight. What puzzled experts most was the uneven nature of the activity. Instead of a steady glow, SWAN tracked bursts, short-lived outpourings of gas, as if the nucleus were riddled with fissures. These episodic releases hinted at structural weakness, the kind that can transform a comet into a fragmentation event without warning. Fragmentation is far more dangerous than a stable flyby. A single body may split into multiple fragments, each following slightly different paths. To observers on Earth, this multiplies uncertainty. A predictable orbit becomes a cluster of possibilities. Some fragments may dissipate harmlessly, while others could veer closer to planetary bodies. Astronomers compared the situation to a shattered glass pane, where each shard scatters light in unpredictable directions. But Swan's discovery did not remain confined to professional circles. Almost immediately, amateur astronomers took notice. Word spread through mailing lists, forums, and social media groups dedicated to sky watching. Small backyard observatories across continents swung into action. Equipped with modest telescopes and sensitive cameras, citizen scientists began recording outbursts, verifying timings, and providing crucial ground-based data. In a matter of hours, what began as a solitary ultraviolet signal grew into a global collaboration. The strength of this citizen involvement cannot be overstated. Professional telescope time is scarce, booked months in advance for planned projects. A sudden ultraviolet alert leaves scientists scrambling to secure instruments. In such moments, amateurs fill the gap. Their observations, though sometimes dismissed in the past, have repeatedly proven vital in confirming activity patterns. In this case, their data showed a surprising trend. The outbursts coincided with rotational changes in the comet's spin, suggesting that jets of gas were physically altering the object's orientation. The ultraviolet detection also opened doors to new kinds of modeling. Scientists began simulating how hidden fissures in the nucleus could evolve, how sunlight penetrates layers of dust and ice, and how stress fractures propagate through fragile cometary structures. Each burst of ultraviolet light told a story of internal struggle, of a body being torn apart by the very star it orbits. Yet, amid this technical pursuit, one haunting possibility emerged. What if a future detection of this type comes too late, and the fragments are already inbound? Unlike asteroids, which often reflect sunlight steadily and allow gradual tracking, volatile comets can transform in days. A quiet object one week may become a roaring, unpredictable source of fragments the next. Ultraviolet alerts give us precious time, but only if networks are ready to act the instant they appear. Not all visitors knock invisible light. Some announce themselves with invisible signals, waiting for us to listen. If this ultraviolet alarm was only the beginning, what stranger messages might still be hiding in the spectrum? Stay here as we reveal everything. 3. I/ATLAS. Carbon-rich, nickel-spitting, iron-absent. It did not look like an ordinary comet from the start. When 3 I/ATLAS appeared on observational charts, astronomers immediately noticed one unmistakable trait. Its orbit was hyperbolic, meaning it was not bound to our Sun. This was no local wanderer returning on a long-period arc. It was an interstellar traveler, a body formed in a distant system, now just passing through. For researchers, every measurement became a once-in-a-lifetime chance to study matter that had never belonged to our solar family. The first surprise came from the chemistry. Using the Very Large Telescope and the James Webb Space Telescope, scientists detected an unusually high abundance of carbon dioxide, far outpacing the water vapor that normally dominates cometary emissions. In most comets catalogued within our system, water sublimation is the driving force of activity. Here, however, CO2 was the main actor. The imbalance suggested that 3 I/ATLAS had formed in a colder environment than Earth's neighborhood, perhaps at the far edges of another star system where carbon dioxide ice was more stable than water ice. As if that anomaly were not enough, spectrographs revealed the presence of atomic nickel streaming out of the object. Grams per second of the metal were escaping into space. On its own, nickel was not shocking, but the absence of its usual companion, iron, left researchers scratching their heads. In most comets and asteroids, nickel and iron are bound together, reflecting the building blocks of planet formation. To see one without the other hinted at exotic conditions in the comet's birthplace. Some theorized that chemical fractionation in another protoplanetary disk had separated the two metals, leaving nickel-rich regions with little iron content. Others suggested surface weathering processes unique to interstellar travel had altered the balance. Rotation added another layer of mystery. Instead of spinning in a steady rhythm, 3I/ATLAS exhibited a tumbling motion. The orientation of its jets seemed to change unpredictably, sometimes pointing away from the sun, other times sideways, as though the body itself were lurching. This chaotic spin not only complicated modeling of its trajectory, but also suggested that internal mass distribution was uneven. A fractured core, riddled with voids or layered by different materials, could explain such erratic behavior. Then came the matter of its tail. Unlike most comets that grow a single, well-defined tail, 3I/ATLAS showed evidence of splitting. Multiple filaments streamed outward, some fading quickly while others persisted. At times, observers reported the tail appearing braided, as though strands of material were being pulled apart by subtle forces. Each split hinted at new jets erupting from beneath the surface, driven by volatile reservoirs, breaking free. It was a portrait of instability, a traveler carrying deep scars from its birth environment. The scientific implications were immense. By analyzing its chemical output, astronomers could infer conditions in another solar system billions of years ago. A carbon-heavy, water-poor composition implied a nursery colder and darker than our own. The nickel signal suggested differentiation processes unlike those that shaped Earth's formation. And the absence of iron, if confirmed, might force a rethinking of how metals distribute in young planetary disks. Every measurement became a breadcrumb leading back to an alien world we will never see directly. For many scientists, 3I/ATLAS felt like a time capsule from across the galaxy. Unlike Oumuamua, which slipped past too quickly for detailed study, this object lingered long enough to allow spectroscopy, imaging, and modeling. Each night of observation added to the puzzle, transforming the comet from a distant curiosity into a key piece of evidence in the story of planetary evolution beyond our star. A chemistry that shouldn't exist for a comet this bright was only the beginning. What happens when such a volatile stranger directs its unstable course toward the neighborhood of another planet? Let us tell you. Mars as laboratory. It was not Earth that found itself in the spotlight this time. As 3I/ATLAS swept deeper into the inner solar system, another planet suddenly became the stage, Mars. From its red deserts to its thin atmosphere, the planet offered scientists a rare opportunity. For the first time, an interstellar visitor would pass close enough for orbiters and landers already stationed there to watch the event unfold. The earliest signs were caught by spacecraft circling Mars. The Mars Reconnaissance Orbiter, equipped with sensitive ultraviolet instruments, detected a sudden flare in brightness. Over a matter of days, the comet doubled in intensity, its tail stretching and then splitting into multiple streams. Unlike Earth-based telescopes, which had to peer through the thick blur of our atmosphere, Mars provided a clear, unobstructed vantage point. For researchers, it was like opening a new laboratory window onto an experiment they could never stage themselves. This unique geometry sparked a flurry of activity. Mission teams scrambled to adjust observation schedules. The ExoMars Trace Gas Orbiter fine-tuned its instruments to sniff out the chemical makeup of the gases streaming from the comet. Meanwhile, rovers on the surface prepared to scan the sky. Though designed for geology and surface exploration, even their cameras could contribute to understanding how fragments scattered through the Martian atmosphere. In effect, every machine on and around Mars became part of a coordinated, planet-wide observatory. The risks, however, could not be ignored. Astronomers plotted the comet's trajectory with increasing precision, but fragmentation added uncertainty. A small deviation could send shards barreling toward the planet. On Earth, a strike of this kind could spell disaster. On Mars, it represented both a danger and an unparalleled chance to study impact physics. With its thin atmosphere, Mars would not cushion incoming fragments as Earth does. Even modest pieces of debris could carve craters, releasing plumes of dust visible from orbit. If any impact occurred near active landers, it might provide the first direct sampling of interstellar material deposited on another world. Planetary protection protocols suddenly took center stage. Space agencies have long worried about contamination. Both ways. Introducing Earth microbes to Mars is one fear. Bringing Martian material back to Earth is another. But this time, the concern was reversed. What if interstellar debris landed on Mars? Would it alter the pristine record of Martian geology, confusing the search for indigenous signs of life? Scientists debated fiercely whether to treat such an event as contamination or as a gift of new science. Amid the technical planning, the wider public began to take notice. Mars has always captured imagination, from the canals once drawn on 19th century star maps to the dreams of colonization today. The idea of a comet possibly interacting with Mars electrified both professionals and enthusiasts. Social platforms buzzed with speculation. Could astronauts someday walk to a crater freshly dug by an alien comet? Could samples retrieved from such a site reveal chemistry never before encountered in our solar system? The practical benefits were equally compelling. By using Mars as a test planet, scientists could refine their models of how interstellar objects behave when interacting with atmospheres and surfaces. These insights would feed directly into planetary defense strategies for Earth. If fragments struck Mars, the data on crater size, ejector patterns, and chemical residue would be priceless for predicting what similar events might look like here at home. Mars, in this moment, became both shield and laboratory, absorbing what Earth hopes never to face. What does it mean when a strange visitor chooses Mars as its next waypoint? Perhaps that the universe is giving humanity a rehearsal on a distant stage before the real performance begins closer to home. Stay with us to know what really happened. Apophis, OSIRISAPEX, and a new playbook. The calendar already has a date circled in red, April 13th, 2029. On that day, the asteroid Apophis will glide closer to Earth than many of our satellites. For years, its discovery stirred panic, with early calculations suggesting a collision was possible. While those fears have since been ruled out, the sheer closeness of its pass makes it one of the most significant natural events humanity will ever witness. For astronomers, this is not a threat anymore. It is an opportunity, a chance to turn fear into preparation. Apophis is massive, nearly 370 meters across, with the power to unleash destruction on a continental scale if it ever struck. When it passes within 31,000 kilometers of Earth, our planet's gravity will not leave it untouched. Tidal forces are expected to alter its spin, fracture surface material, and possibly even shift its orbit slightly. This interaction will provide real-time data on how asteroids behave under Earth's gravitational pull. No simulation or laboratory experiment can substitute for the spectacle of a near miss unfolding in plain sight. To capture this unprecedented event, NASA has reassigned the OSIRISAPEX spacecraft, now renamed OSIRISAPEX after successfully returning samples from Bennu. Instead of retiring the probe, engineers set it on a new trajectory to rendezvous with Apophis during its close approach. Its mission? To record, in exquisite detail, the reshaping of an asteroid as it brushes past our planet. Cameras and spectrometers will map surface changes, while instruments will measure dust and debris lifted by tidal stress. For the first time, we will watch an asteroid's geology evolve in real time. The lessons extend far beyond Apophis itself. Every data point will strengthen planetary defense models. By understanding how asteroids fracture, rotate, and respond to gravitational stretching, scientists can better predict the outcomes of deflection attempts. For instance, if humanity were ever to push or nudge an incoming body off course, knowing whether it will hold together or break apart becomes crucial. A fragmented asteroid can turn a single target into dozens of threats, scattering destruction across multiple regions. Global collaboration is already in motion. Space agencies in Europe, Japan, and elsewhere are aligning their observation plans with NASA's mission. Ground-based telescopes will track Apophis before, during, and after its flyby, measuring how its orbit shifts. Radar arrays will bounce signals off its surface, mapping shape and rotation with remarkable precision. For once, the world's scientific community will act as a single observatory, united not by fear, but by anticipation. Yet coordination is not only scientific. Policymakers are quietly discussing how to integrate the findings into long-term defense strategies. If Apophis's encounter confirms theories about tidal reshaping, it may provide the strongest justification yet for funding planetary defense programs that, until now, have struggled to secure resources. For some governments, the asteroid represents more than data. It represents accountability. No leader wants to be the one who ignored the warning signs should another object, larger and on a collision course, emerge from the darkness. But behind the technical triumph lies a deeper question. Is humanity ready to move from watching to acting? The surge of recent discoveries, some small, some worryingly large, has highlighted how thin our margin for error truly is. Apophis is a dress rehearsal, a reminder that while we may not control the timing of celestial encounters, we can control our readiness. Proposals for kinetic impactors, gravity tractors, and even nuclear deflection methods have been drafted, but few have been tested. The 2029 flyby may finally provide the urgency needed to fund and implement such measures. Public perception will play a major role. For many, the sight of Apophis streaking across the sky will be a source of awe, a moment when the cosmos feels both close and terrifyingly real. But awe can quickly shift to anxiety if communication is unclear. Governments and agencies must strike a balance, presenting the event as a scientific milestone without downplaying the fact that similar objects could one day pose real danger. Outreach campaigns, live broadcasts, and transparent data releases will be essential in shaping public trust. The narrative must evolve from "we survived" to "we are prepared." To make that leap, humanity must embrace Apophis not only as a spectacle, but as a warning wrapped in opportunity. If this event does not galvanize real preparation, then the lesson may be lost, leaving us vulnerable when the next celestial visitor decides not to miss. Are these multiplying giants a warning sign from the cosmos, or simply the start of discoveries we were never prepared to face? Share your thoughts in the comments.